Hi everyone. In this video, I'm going to be going over an example for when we have an R by K contingency table and we end up doing a chi-squared test on it. So let me just talk about the context here first of all. We're talking about contingency tables. That automatically means that we're talking about categorical data because a contingency table is just a way of, in a visual way, showing the different frequencies of different categories across a couple of dimensions. So we have two dimensions we're thinking about here. We've got rows, we've got columns. And the idea is each of those is a variable with several categories maybe, or just two categories, or three or four, however many categories. And then we can look at all the cells of the contingency table and answer questions about whether the two variables represented in the rows and the columns are associated with each other or whether they're independent of each other. The first thing to think about here is that the null hypothesis, when you've got an R by K contingency table for categorical variables, is the two variables are independent of each other. That is the null hypothesis, is that they are not associated with each other. We have other ways of thinking about the null hypothesis that are kind of more complicated, involving compound null hypotheses, but for the purposes of this problem, we're just going to think about the null hypothesis being that the two variables, the one that you see in the columns and the one that you see in the rows, are independent of each other. And then we can think of the alternative hypothesis as there is an association between the variables. So that's the first step for thinking about how we're going to do this hypothesis test. Let me show you guys an example problem. So this is from your book again, and the question is acupuncture effective on back pain? And so we've got different patients assigned to one of four groups. They're assigned randomly to one of four groups, different kinds of treatment for this back pain. We have standardized acupuncture. We have acupuncture that was individualized. We have simulated acupuncture, where they're just like using, like poking them with toothpicks, but not actually breaking the skin. And then a fourth group was not getting any acupuncture. They just received other medical care, so did not include acupuncture. So by my count here, we have four categories for the type of medical care received. So that's one of the categorical variables that we'll be thinking about, is what kind of care they received. The other one is about the outcome. So the researchers recorded whether or not each patient improved by at least 3 points on this Roland Morris Disability Questionnaire scale. So there is a scale, presumably some kind of numeric scale, that they reported their improvement on, but the actual variable that we're looking at is whether or not they improved by at least 3 points on that scale. So that makes it a categorical variable. Either they did improve by that amount or they didn't improve by that amount. So we're going to end up with a 4-column, 2-row contingency table here. We could also do it with 4 rows and 2 columns, but it doesn't really matter which way we go. So this time, 2 rows, 4 columns to show off this data. So here's what the data from the book looks like. We've got our 4 categories for the type of care along these different columns. We've got 2 categories for whether they improved in the rows. So we have 8 different cells in the middle here altogether. And then, as usual, our second step after working out the null and alternative hypotheses is to actually write out the test statistic. So hypothesis tests always have test statistics. They are different from test to test. That's the point of them. The test statistic for the chi-squared test for an R by K contingency table looks like this. So I'm writing this little s next to the chi-squared to show that this is the test statistic. This is something we're getting from the data. And we'll write this summation here, and I'll just, to make it easy, write all cells underneath the summation symbol to say that we're doing this for all 8 cells in the center of the table here, obviously not including the totals. And it's the same exact formula as you have for the chi-squared goodness of fit test or a 2x2 contingency table. The only difference between these different scenarios is that we're going to change the degrees of freedom when we go to the chi-squared table. So it should look familiar to you guys. It's observed for each cell minus expected for each cell divided by the expected value for each cell. So the first step then, we have the observed values. Those are what I put in the blue box there. But we need to think about what the expected values are for each of these cells. And the quick and easy way to do it is to look at the row total and the column total and divide by the total. So I'll show you what I mean by that. First of all, we need to get the grand total here. It's not listed. It should be in that spot there in the table. You can add it up either horizontally or vertically. It's going to be the same number, but it's going to be 583. That's the grand total, what I called the total before. So we're going to need that and to calculate the expected frequency for each of the cells in the table here. So let's start up here in the upper left corner. 92 is the observed frequency. The expected frequency is going to look like 141 times 350 divided by the total. That's how we're going to do it every single time. So in this cell here, I'll just put a little arrow. We're going to write it as 141 times 350 over 583. That's the expected value for that cell. I'll call it cell 1. When I work that out, I get 84.6, which I'll just put in parentheses so that we know it's the expected value, not the observed value. And then I need to just go ahead and do the same thing for all of the other cells in the table. So the next one I might look at would be here, which is going to be 147 for the column total, still 350 for the row total, and still 583 for the grand total. So 147 times 350 over 583 equals 88.3. When I do this for all of the 8 cells in this table, then I'm going to have those 8 observed values, 8 expected values, and I'll be able to do this chi-squared test statistic. And then here's what the calculation looks like. 92 minus 84.6, that's observed minus expected in the first cell there, divided by expected, plus 96 minus 88.3 squared over 88.3. So same thing, observed minus expected squared divided by observed. 90 minus 91.2 squared over 91.2 plus 72 minus 85.8 squared plus, now we're on the bottom row between the two, 49 minus 56.3 squared divided by 56.3 plus 51 minus 58.7 squared divided by 58.7 plus 62 minus 60.7 squared divided by 60.7 plus 71 minus 57.1 squared over 57.1. So then the total on that is like 8.92. So that is the value of my test statistic, the chi-squared test statistic. There it is. That's what I'm going to have to take to the table. But as usual, before I go to the table, I've got to know the degrees of freedom that I'm looking up in the table. And for a R by K chi-squared table, the degrees of freedom is always going to be R minus 1 times K minus 1. I've got 2 rows, I've got 4 columns, so that works out to 1 times 3, or just 3. So now I'm going to go to the table with this test statistic and this degrees of freedom. Just as a reminder, when you have an R by K table with more than just 2 rows and 2 columns, then you're never going to be doing a directional hypothesis. It's always going to have to be non-directional, because there's lots and lots of different ways that the alternative hypothesis can differ from the null hypothesis. Okay, so here's the table for chi-squared. The test statistic from the last page was like 8.92, and the degrees of freedom was 3. So we're going to be looking along the degrees of freedom, the third line in the degrees of freedom right here. I'll zoom in a bit. And we're looking to see where we can find that 8.92 from the test statistic. And it turns out it's right there in between 7.81 and 9.84. That's the range that our test statistic 8.92 is in. And so that means we go to the corresponding probabilities up here. And recall, this is going to be for sure a non-directional test because there are so many categories in the 2 categorical variables. And the column headings, according to the text up here, say they are non-directional. Already, we don't need to do anything to them. Unlike in the case of the t-test, where if we want to get a non-directional test, we have to actively multiply the upper tail probability by 2. We're not doing anything like that here. What we get from the table is going to be the non-directional p-value. So we're going to say that our p-value is between the values of 0.02 and 0.05. Again, if we're using alpha equals 0.05 as our significance level for this test, then we can say that indeed the p-value is less than alpha, which means we reject our null hypothesis. And if you'll recall, the null hypothesis was that these 2 variables, the type of treatment and the outcome, were independent of each other. And we're rejecting that. We're saying there is some association between the type of treatment a person received and what their outcome was like.